Today we're going to be talking about Einstein's postulates of the special theory of relativity. So first we need to have a look at a definition of a term. The term is inertial reference frame. So an inertial reference frame is a location in space and time where all observers are moving with constant velocity. So there's no acceleration. The velocities of all of the observers are constant. Now, a reference frame, you might remember, if we look at some different situations where a person might be throwing a ball up and down in a car. If the person in the car, driving along, the person in the car sees the ball go up and fall under gravity and be caught back in their hand. They see it travelling straight up and down to them. An observer on the side of the road sees the ball being thrown up in an arc and being caught as the car is moving along. So the ball, from an observer outside of the car, standing stationary on the side of the road, sees a different event occur, sees a different course of action. They're both right. They're both right in what they see, but it's just a different view that each of those two have. They are, however, within inertial reference frames. So the observers are moving with constant velocity. So the laws of physics are the same in all inertial reference frames. This is Einstein's first postulate for his special theory of relativity. That's saying the laws of physics that the person is in the car they're seeing gravity acting on the ball, they're seeing the gravity pulling the ball back down to their hand and them catching it, and so is the observer on the side of the road. However, they're seeing the ball being launched with some horizontal velocity as well, the horizontal velocity of the car. So they've got the horizontal velocity as well, but the same laws of physics are acting on that ball. They're both seeing the same laws of physics being acted on, because they are in an inertial reference frame. They're in an inertial reference frame. They are seeing the car is travelling at a constant velocity. The car is not accelerating. If the car was accelerating, that is a non-inertial reference frame. That's not an inertial reference frame, and the laws of physics would appear to be different to both observers. Both observers. The person inside the car would see the ball being moved backward if the car was accelerating forward, positively accelerating forward, gaining speed, gaining velocity. The person would throw the ball up, but the car would be moving with increasing more velocity, and they wouldn't be able to catch the ball straight away. It would fly way back for them. So this is Einstein's first postulate that the laws of physics are the same in all reference frames. The second postulate that he has is the speed of light in a vacuum is the same in all inertial reference frames. So regardless of what velocity you are travelling at, Einstein said that the speed of light is constant, it's the same value. So it's given the letter c, this variable, this constant c, and it's approximately 3 × 10 to the 8 metres per second. This has been measured with increasing accuracy over the years, and this is the most accurate value that's been settled upon. Now, just as a note, a postulate is an assumption where that can then inform more logic. So a postulate is something that is presented as an assumption, as essentially a hypothesis, and then that hypothesis can be tested later on using experimental techniques based on the logic and the other ideas that follow from these two postulates. So these are the two postulates that underline Einstein's special theory of relativity. If we have a look at two examples of Einstein's two postulates, we look at the first example here of the first postulate. That's the laws of physics are the same in all uniformly moving reference frames. So here we've got the spinning of the Earth, in most cases, has no bearing on being able to throw a ball to a friend and catch it, despite a point on the equator moving it over 1,600 kilometres per hour, 1,600 kilometres per hour. So the Earth is rotating all the time, but we don't sense that, we don't feel it. We would certainly feel something different if the Earth wasn't rotating, but the Earth's rotation doesn't affect our day-to-day life very much at all. We can still throw and catch things. The laws of physics are the same for us here on Earth in our everyday lives. However, there are some occasions and some situations where the spin of the Earth does affect certain aspects of our life here on Earth. The fact is that the spinning of the Earth is not an inertial reference frame. And the reason for that is if we've got a point on the equator moving at over 1,600 kilometres per hour, it moves very, very rapidly, but the Earth as a sphere is rotating at a constant rate. There are the points on the poles aren't moving at all. They're only rotating on the spot. So as you move further and further away from the equator, the actual motion around the sphere of the Earth gets slower and slower because the circle that's being traced out by that person's movement being on that point on the Earth is less and less of a radius. It's less and less of a circumference. The largest circumference, the largest point, or the point that has to travel the greatest distance, is on the equator, and it has to do it in 24 hours because that's the rotation of the Earth occurs once every 24 hours. Moving further away, we have to do smaller circles, but still the same time frame, once every 24 hours. So for that reason, the velocities are less and less. So depending where you are on the Earth, the velocity that you're travelling at might be different. So unless you are throwing causing motion to occur in that circle, you're exactly right on that circle, you are going to be in a non-inertial reference frame. Throwing it further away from the equator or closer to the equator is going to change where the ball is and how fast the ball would be travelling with respect to the Earth. So, when does this spinning of the Earth affect the laws of physics? Well, weather is has a major impact, or is impacted majorly by the spinning of the Earth. Cyclones and storms all rotate in certain ways. It's called the Coriolis effect, based on the spinning of the Earth, and that's due to the fact that the Earth is a non-inertial reference frame. Weather is a massive, much larger situation than we would normally see day to day, as in throwing a ball or driving a car or something like that. So that's when we see this sort of effect. It also occurs when firing projectiles over very, very long distances, such as long-range artillery that was used perhaps in World War II. The cannons that they used were firing many 20 or so kilometres, 25, 30 kilometres, and the actual motion of the projectile curved depending on whether it was being fired towards the equator or away from the equator, and by what degree. So that's when the laws of physics do seem to change for different observers. The observer of the person standing on the Earth watching projectiles move, projectiles like water droplets, rain droplets, or the rain droplets themselves and what they're observing. The second example I've got here relates to the second postulate, the speed of light, and it's called the invariance of the speed of light. Invariance means it doesn't change, it doesn't vary. So if we're looking at throwing a banana out of a car, and the car is travelling at 60 kilometres an hour, we throw the banana directly out the front of the car. If we've got an observer on the side of the road, they're going to see the banana travelling at a speed greater than 60 kilometres an hour, because we've got the velocity of the car plus the velocity of the banana that's been thrown forward out of the front of the car. So if that person threw it at say 10 kilometres an hour, then the observer would see it at 70 kilometres an hour, the 60 kilometres an hour that the car's travelling, plus the velocity that it was thrown at. So the banana would appear from an observer on the side of the road to be travelling much or slightly faster than the car. The observer, what does the thrower observe? Well, the thrower is going to observe it being thrown at the velocity that he throws it at, whether it's 10 kilometres an hour. So the difference, the observer on the side of the road views it moving at 70 kilometres an hour, and The thrower observes the banana being thrown at 10 kilometres an hour. So that's an analogy where we're looking at an everyday object, but when we look at light, Einstein's second postulate says that the speed of light doesn't vary. So let's see how this affects what we might know. So the driver of the car turns his headlights on. He turns his headlights on. What speed does the driver see the light travelling at? Well, obviously, he's going to see it travelling at c, at about 3 times 10 to the 8 metres per second. He's going to see it travelling at that. He is in the car, he's turned his lights on, the light goes out, he sees it travelling at 3 times 10 to the 8 metres per second. But what about the person standing on the side of the road? If we had a look back at our banana analogy, it should be c plus 60 kilometres an hour. The speed of light plus this amount. But Einstein said that no, the observer on the side of the road sees it travelling at exactly the same velocity, at 3 times 10 to the 8 metres per second. And this went against all of the previous thought that light needed some sort of medium to travel through, even in space. And this medium was called the ether, or the luminiferous ether. Which luminiferous sort of means that the ether that light travels through, this thing that light travels through. And if you look at an experiment called the Michelson-Morley experiment, that disproved this luminiferous ether, because it was thought that there was, if there was an ether, there would be a velocity to the ether, so it would flow. And they set up an experiment where there was light travelling across this supposed velocity, and also light travelling towards it, and looking to see if there was a difference in the light reaching different detectors and the velocity of the light. Because surely, if it was travelling against the luminiferous ether, it would be slowed down. The light would be slower. Einstein thought that this was clearly wrong. He thought, what if I was travelling at the speed of light and I turned my car's lights on? What would happen? Would I see the light wave sort of frozen there, slowed down? He postulated that, he hypothesised that no, I wouldn't see that. I'd see it travelling at the speed of light. And it was proven that the luminiferous ether did not exist via this experiment, this Michelson-Morley experiment. So taking what we know now about Einstein's two laws, we can look at a special case called the relativity of simultaneity. So it's saying that the dependence of something appearing to happen at the same time, for it to be simultaneous, to happen at the same time, depends on what where the observer is. And we've seen that the velocity of a banana can determine whether or not can vary depending on the observer. So we can have a look at an instance involving light. So if we consider a train carriage that's moving at some velocity v, so it's moving, it's not accelerating, it's in an inertial reference frame where all of the observers in the situation are going to observe a constant velocity. There's a light source in the centre of the carriage that can be turned on, and light can radiate out from it. The light that's radiated out can trigger the front and rear doors of the carriage to open if that light reaches the doors. So if it hits the doors will open. So we can have a look at two cases, the observer inside the carriage and the observer outside the carriage. So just looking at the observer inside the carriage is moving at a velocity v, but the person inside the carriage is stationary right at the centre, so they're going to see the light radiate out. It's that light red lines are the light pulse that's radiated out from the light source in the centre. They radiate outwards at the same velocity, the speed of light, and they both strike the doors at the same time. We can see that makes sense. It's right in the centre, the light radiates out from the centre at the same velocity, so the doors will open at the same time. That's what the observer inside the carriage will see. They'll see the light radiating out, hitting the doors at the same time, the doors open at the same time. They are simultaneously occurring. for the observer, they see the doors open simultaneously. If we've got an observer outside the carriage, however, they will see something very different. They will see something very different. So the carriage is moving along at some velocity v. The light pulse is emitted just the same as the other observer would see, but this observer is outside the carriage. They are stationary and watching the carriage move along at the same time. So after the first instant, the carriage has moved slightly to the left, to the right, sorry. So what we see is the light source moves to the left, but this light pulse that has been emitted out is still still has the centre of where the carriage was before. The light is radiating out from that point, and you can see that because the carriage has shifted to the right because of its velocity, it has moved the light pulse, or the light pulse is moved from within the carriage and is actually closer to the rear door than the front door. If we see, the light pulse continues outward and will strike the rear door first. It will strike the rear door first, whilst this light pulse on this side of the carriage is still trying to catch up to the carriage to the front door of the carriage that's moving at that velocity. So the observer on the side of the road will actually see the rear door open first before they see the front door open. And this is the relativity of simultaneous. This observer will see the doors open simultaneously. This person here is going to see the rear door open first. They're going to see this one open first. And that's due to, this is a thought experiment that Einstein came up with, where to demonstrate just how unintuitive these ideas are. But all of the experiments that have been done have not disproved Einstein's two postulates. They've only supported it. All of the evidence that has been gathered over the past 100 or so years has only assisted to support Einstein's two postulates, Einstein's special theory of relativity.